Okay, here is a picture of this piece of cardboard, 16 by 8, and we have to cut squares of equal size from each corner, bend up the sides that remain to form an open box, and find out what size these squares should be to create a maximum area. And just so you can visualize it, of course, if this length is 16 and we cut an X out here and an X out here, this dimension from here to here will be 16 take away 2x. And likewise for the width of the box or the base will be 8 take away 2x's. And so the box is going to look like this: 16 minus 2x by 8 minus 2x, and this height will be x. So the volume of the box will be represented by this formula right here: length times width times height. And what we want to do is take the derivative of v with respect to x. We could multiply this all together and differentiate term by term, or we could do what I did here. I distributed this x over this factor and then use the product rule. So I'm not going to go through the product rule, but in the end, this is what I got when I simplified everything. And I want to know, when does that equal 0? That will give us our critical numbers. And by the way, I did take the second derivative here. We can use that to tell us whether the critical numbers that we end up with are going to generate local maximums or minimums. So here I set the first derivative equal to 0. I noticed that every term was divisible by 4. I tried to factor it, but saw quickly that it didn't factor. So I used the quadratic formula and got 24 plus or minus the square root of 194 over 6. Now, one thing that you need to realize, I meant to mention this on the first board, is that the domain of this function has to be something like this. Because if you cut out more, you can't cut out more than a 4-inch square, even a 4-inch square from each side, because that would totally obliterate the width of the box, which is 8 inches. So there's the domain of the function, which means we have to reject this guy. And if we put 1.678 into the second derivative, we get a negative number, which means the tangent lines are decreasing in slope, which means that this critical number generates a relative maximum. Because in essence, the curve is concave downward at that point, relative max. Now, I will share my screen real quick. Go to Desmos, and here's the volume function right here, as depicted on the whiteboard. And here I've set up a table of possible x's. And you can see that as x starts at 1, we get a volume of 84. And it seems to be increasing until we get to 24 minus the square root of 194 all over 6. 98.53045 is just a little bit bigger than this 1.678, which was an approximation to this. And after 1.67 at 1.8, we're starting to go down in volume. And that's depicted by this graph up here. So this point right here is this square root of 24 minus the square root of 194 over 6. And there's the volume that generates 98.534. So there you go. Hope that helped. I'll stop sharing and end the recording.